Okay, hello everybody. Here is your video key for the third and fourth pages of problem set 0. Number 9, you just make up your own piecewise function. So yours might look completely different than this. I made mine sort of simple, just the line y equals x, y equals 2, and the line y equals 2x. And then I defined it. You got to give it a domain for each of those pieces, so I'm going to use x when x is less than 0. I'm going to use the line y equals 2 between 1 and 4 for x, and I'm going to include 1 and 4. So graphically that's going to make solid dots as opposed to holes. Actually, hold on. It's just less than 4 here. So I'll have 1 solid dot, 1 hole, and then 2x where x is greater than or equal to 4. And then you just graph these three different lines, the line y equals x, y equals 2, y equals 2x, on these x values. So here we have that. And then the line y equals x for x less than 0. So when x is 0, if I plugged it into the line y equals x, let's see if I know how to point on here. Right, so if I plug in x equals 0 into here, I would get the point 0. But since 0 is not inclusive, then the point 0, 0 does not exist. So it's a hole at 0, 0 for the line y equals x. And then it's for x less than 0, so it's going to go this way, having the point -1, -1, -2, -2, -3, -3, etc. Okay, and now looking at the line y equals 2, I'm going to graph that just between 1 and 4. So here's 1, 2, 3, 4, and the line is y equals 2, so 1, 2. My 2's don't look very good on here. There we go. And then, so this is just a horizontal line. Once again, since this is or equal to, it's going to be a filled-in circle. At x equals 1 and at x equals 4, it's going to be an open circle. And so the y value is 2 the whole time, so I can just put a closed dot here, an open dot there, and connect those two pieces. And then finally we have the line y equals 2x starting at x equals 4. So right here, when x is 4, I would get a value of 8. So I'm going to start at the point 4, 8, and then just draw a line that has a slope of 2. You can either you could plug in 5 if you want and get another point and then just connect those 2 points. You could count your slope, which is 2, so you go up 2 over 1, however you want to do that. But in either case, I'm going to start up at 8. This is not going to be drawn to scale. We're just going to call that 8. And then from there, draw a line with a slope of 2. Really, you should draw a second point for that line. There's a cleaner version on the key that I have written out for you. Number 10, we're given the graph and we have to write the piecewise function. So I'm going to look at this in two different pieces essentially, and I'm going to look at the red piece first and figure out what that line is. If you notice, this kind of has a weird scale. This is 5 out here, so every one of these is a half. That's half, 1, 1.5, 2, 2.5, 3, etc. Which means our y-intercept right here is 3. And then you can count your slope from this point to, I'm going to go up to that point because that's a clear point, I think. So it's up 1, 2, 3, 4, 5, 6, but over 1, 2, 3. So my slope is 2. So the equation of that line is 2x plus 3. So my function then is f of x equals, I have two different pieces because there's two different lines, but 2x plus 3. And then just look at what x values this is graphed for. Well, it starts at -3, but not including -3 because there's a hole there, and it stops at x equals 1. So then the domain you write over here is just -3 less than x less than 1. Notice the notation on this. A lot of students have a tendency to kind of make up their own notation and like They don't write f of x equals right here. They don't put a brace. Sometimes they write y equals inside the brace multiple times, but that's what this single f of x equals does for you, so you don't need to write it more than once. And then our second line is just the horizontal line y equals 5. And those are both open circles as well, so it's between 1 and 5 for x, if you look at the graph. Number 11, graph the absolute value of x and define it piecewisely. So here we're just going to take another graph. Absolute value of x, you should know, looks something like that. But you can see how really the absolute value function is just two different lines. And perhaps intuitively you could understand that one of the lines is just the line y equals x, and the other line is the line equals y, or y equals negative x. And so here's the line y equals x right here. And that is graph starting at x equals 0 and then going numbers bigger than that. And so I'm going to say it's equal to x for x greater than or equal to 0. And then right here is the line negative x. And that is graphed starting at 0 and going left. So you can say x less than 0. In my domain restrictions over here, it wouldn't matter which one I said is or equal to, but definitely the point 0, 0 does exist on this graph, so you got to make at least one of these or equal to. Technically, it would be okay if you made them both or equal to, since it's the same point. But if the points were ever like one above another, then you got to make sure you don't make them both or equal to, otherwise it would no longer be a function. Number 12. Find the domain and range of this and then sketch the graph. You should know the domain of an absolute value function is all reals. So in interval notation, negative infinity to infinity, or you could use the all real symbol. I'll give you a reminder of what that is. So one or the other, you don't need both of those. And then the range, hopefully you know the vertex of this is going to be negative 7, negative 4. And so our range is going to go down to negative 4, that comes from this number right here. And then it goes up forever, and it's going to include negative 4. So negative 4 to infinity, because that's just where the vertex is. And then, so we can start at the vertex, negative 4, negative 7, not drawn to scale. And then that just has a slope of 1 in both directions. Really find another point there, and you can make it look nicer. I'll make that look a little nicer, because those should definitely have like opposite slopes. Same steepness. Number 13 defines an exponential for you. Find the domain and range of an exponential. So the domain is all reals again. And the range, you should know, is 0 to infinity. You cannot raise a number to a power and get 0. You can get really close to 0, and hopefully graphically you know what an exponential looks like, and then you can make a connection between the graph and what the domain and range are. Okay, complete the following properties. This is just saying, hey, if you multiply two numbers that have the same base, then you add the exponents. When you divide, you subtract the exponents. If you divide two numbers that have the same base. These two things are equal to each other, and this is called, we call this power to a power, if you've ever heard that, and that you just multiplied the exponents together. Part D, that's the same as saying A times B both to the x power like that. And then similarly on E for division, you can just, if you have a fraction, you can just raise both parts of your fraction to the exponent separately. So those are the main properties of exponents. Page 4. So rewriting logs into exponential form and exponentials into log form, I think, is a really important thing. It helps when you solve problems. It helps really in many cases. Some people, like when you solve an equation involving logs, they'll like do e, they'll raise both sides like e to the both sides power. But if you just use the definition of logs, I think it helps you understand it a little better, and I'll show you what I mean when we get down to 17a. But 15, so the way I explain this is you should know in an exponential that this b right here is called your base. And if you know what the definition of a log is, hopefully my students from last year at least know, a log, one word definition is, and the answer is, an exponent. So a log always equals an exponent. So when you're writing this in log form, it's log. The base of your log is the base of your exponential, which is base b. You know a log is an exponent, so that's what your log equals, so it's always going to equal x. And then the only other thing that there is the y, and so that's what you're taking the log of. Okay? And that we can use that same logic on 16. The base of the log is the base of the exponential, c. What is a log? Well, it's an exponent, so my log equals my exponent, so equals g. So it's c to the g, and then equals the only other number there, which is the thing you're taking the log of, which is d. 17, solve this for x. This is actually just one step if you just use the definition of logs. So we can change this log into an exponential. Remember, natural log is base e, so my base is e. A log is an exponent. That means this whole thing right here is my exponent. 12t plus 7, and then that must equal x. Hey, solve for x, I'm done. There's nothing else to do there. On this one, so we can write this as a log, so it's log base e, which is natural log. A log is an exponent, so it's going to equal 5x, and what are we taking the log of? 8. And then divide both sides by 5, and you get x equals natural log of 8 divided by 5. If you really wanted to, you could use a calculator and get some decimal expression for that, but that's our exact answer right there. Okay, 4 basic properties of logarithms. The product rule, so this is when you have log, whatever your base is, it doesn't matter, of two things multiplied together. You can expand this into two different logs, both containing the same base as the original log, so base c in this case. Log base c of the first number that you've multiplied together originally, plus log base c of the second number. Quotient rule is very similar. Log base c of a divided by b is equal to 2 logs subtracted, so log base c of the numerator minus log base c of your denominator. Power rule, this just says if you're doing log base anything of a number to a power, you can bring that power down in front of the log, so this is the same as n times log base c of a. And then the change of base formula, which is the things people seem to forget the most. So if you have log base c of a, and that's two numbers, and you don't know how to solve it, like for example, log base 2 of 8, you should know equals 3 because 2 cubed equals 8. But if it's log base 4 of 7 equals what? That's saying 4 to what power equals 7, and that's something we don't know. And so you can use change of base and then use your calculator to figure it out. So change of base says, hey, you can do log base anything you want. We would choose base 10 or base e because those are what are on the calculator. So log base b of, so b being anything you want, of a divided by log base b of c. So that's your change of base formula, which is also useful when graphing. Some of your calculators will just let you type it exactly like this now. Some of you have that functionality, some of you probably don't though. But all of you should know change of base. Alright, so use a graphing calculator to graph this. So you need change of base to graph it. You're just going to graph it as y equals either log base 10, which remember you don't write base 10 when it is base 10. It's just understood that it's there. So use change of base so you can just graph it like that. Or you could use natural log of x over natural log of 4. And then in either case, your graph will look roughly like this. We have the point 1, 0. Remember, log base anything of 1 is 0, like log base 4 of 1 equals 0, because 4 to the 0 equals 1. So anytime you have a 1 right here in your log, it equals 0. And then you can also always plug in your base for x, so I'm looking like right here. So if I plug in 4 for x, I'll get 1 because 4 to the first equals 4. So those are two easy points you can get. So we have the point 4, 1. This is at 1. And so a log looks like that. All right, and then number 20, find all the trig values if sine of theta equals negative 3/5 and tangent of theta is negative. Remember, sine is negative in two different places. Sine is your y value, which is negative here. I'll just write negative sine here, and negative sine values there. But then tangent would being less than 0 only occurs in one of those two quadrants. Remember, tangent is sine divided by cosine. In quadrant 3, cosine is also negative, which means tangent is positive. And then here, cosine is positive, which means tangent is negative. So we're looking in quadrant 4 for this problem. So you can just draw some arbitrary angle theta, make a triangle. Here's our theta. And then sine, which is opposite over hypotenuse, would be negative 3/5. That makes this a 4. It's a Pythagorean triple, or just use Pythagorean theorem if you didn't know that and figure it out. And now, from that triangle, we can find all the other things. We already know sine. Cosine is adjacent over hypotenuse. It's a pet peeve of mine when people just write cosine and don't put an angle right here, so make sure you're doing cosine of something. That doesn't make sense otherwise. Tangent is opposite over adjacent, which is negative 3/4. And then I'll write sine because the other three are just reciprocals of these things. So sine is negative 3/5, which then means cosecant is negative 5/3. Secant theta is 5/4. I apologize for my penmanship on some of these things, but I have a nicer version written out that you can look at if you need to. And then cotangent of theta is negative 4/3. All right, and that is it for pages 3 and 4.